So the title of my talk is Estimation of Glass Forming Ability and Mechanical Properties of Aluminium Zirconium Alloy using Molecular Dynamic Simulations. So this is the outline of the talk. So first is a basic introduction to the topic, then the objectives of this work, and then a brief introduction to the methodology and the primary results and discussion, and then conclusion. So basically, this aluminium, zirconium alloy, these are basically come under the
Dr.
bulk.
Sarangi,
Yeah.
Dr. Sarangi,
Yes, yes.
please switch on your camera.
Actually, this limited bandwidth is there. So is it possible I can talk like this?
You can
At least
rejoin it.
you have to switch.
Studied in this work is aluminum zirconium alloy, which is basically a bulk metallic glass. So bulk metallic glasses are a new type of material which is in demand in today's era because of its non-crystalline. They are non-crystalline metallic alloys. Basically, they have amorphous structure and they possess both the properties of the glass as well as the metals, and they have some unique characteristic as compared to the traditional metals and the traditional glass materials. So the unique properties include they have better structural and mechanical properties, they are more resistant to corrosion, enhanced physical, biochemical, biomechanical properties, and they have application in various areas like aviation industry, like the aluminum based amorphous alloys are heavily used in the aviation industry, then automobile industry where the magnesium based amorphous alloys are used, and in medical sector zirconium, titanium and iron based amorphous alloys are being used. So there is actually huge demand of this new type of material, bulk metallic glasses, and since last few years only the research is started in this area. So a lot of some experimental works are existing in this way in this field, but MD simulation works are rare in this field, and MD simulation is basically can give you the details about the the materials structure and property relationships from the atomic level. So we have carried out the work by using molecular dynamic simulations. So basically this work has two objectives. One is the estimation of the glass forming ability of the alloy, and the second one is characterization of the mechanical properties of the alloy under different uniaxial tensile strength. So basically, we want to test its mechanical property, its hardness, strength, etc., and then its glass forming ability, how good it can form a glass. So the methodology here, I'm using molecular dynamics simulations. It's basically a computational work, and molecular dynamics simulation is basically atomistic calculations, and then Newton's equation motions are the first thing to do to solve to get the position and velocity of the each atom with respect to time. So basically we get the time evolution of position and velocity of each atom, and using those velocity and positions we calculate various different properties. So these are the basic steps followed in MD simulation. So prescription of initial position and velocities are done, and after that calculation of force on each atom is done with the help of the Newton's equation of motion, and then the trajectory of each atom is tracked. And then this goes on repetition till the equilibration is reached. And once the system is in equilibrium, then we store the position and velocity to make the analysis runs. So one of the most important thing in MD simulation is the choice of the potential field which is used, because the force is calculated by taking the negative gradient of the potential energy, and the potential energy depends on the type of bond exists in the system. So like here we have taken aluminum and zirconium, so those are basically metallic substances. So for them, the embedded atomic method potential is the best potential which can depict the interatomic potential. So that is been chosen for this work. It's written as MEAM, that is the modified embedded atomic model. That is the potential used for the to represent the aluminum zirconium interatomic interactions. And so this is the brief description about the MEM potential. So basically the equation of the potential is given by this E is equal to sum over I Fi rho I plus half sum over Ij Sij phi Ij Rij. So this basically represents the interatomic potential between the atom I and atom J, and this is the essential part while carrying out the MD simulation. And after that, coming to the results, so here I'm showing you, and the left side is one unit cell of the AlZr3. So the gray color one is the aluminium, and the green color three atoms, they are the zirconium. So that's one unit cell which has a BCC L12 structure with lattice constant 4.37 angstrom. And then we have repeated this unit cell along the X, Y, and Z direction 10 times basically to generate the bulk structure. So right hand side is showing the bulk structure which contains 4,000 atoms in the composition of 25% of aluminium and 75% of zirconium. So this is how the bulk metallic glass are actually formed. So if you can see the figure, four systems are given. First one in the left hand side, it has 300 Kelvin, that is the initial structure, which is a BCC L12 structure containing 4,000 atoms of aluminum and zirconium. So it is at room temperature. So then we heated the system from 300 Kelvin to 2,500 Kelvin to melt the crystal. So on the top, you can see on the left hand side, that is the structure at 2,500 Kelvin. That's the melted structure. And then we carried out the NBT simulation. That means we have equilibrated the system at that 2,500 Kelvin for 1 nanosecond. So that is the right hand side top structure. That's the melted structure. And after that, the melted structure is quenched in a high rate to make the glasses. So you can see here it's a down arrow in the NPT ensemble to reach the 300 Kelvin structure. So basically the right hand side down structure is a bulk metallic glass structure. So bulk metallic glasses are created in that way. That means you heat the crystal in certain rate, and then you cool down the crystal at a very high rate so that they do not get enough time to crystallize and they will form amorphous glass structures. This is what is been approached in the MD simulation to get the final structure of the bulk metallic glass of the aluminum zirconium alloy. So now to study its glass forming ability. Okay, so we have done the, so in this graph I am showing you the potential energy per atom versus the temperature during the heating and the cooling process. So heating means 300 Kelvin to 2500 Kelvin, that is the black curve, and the red curve is cooling process, that is from the 2500 Kelvin to the 300 Kelvin. So the black curve represents the melting curve, that is the heating curve, and you can see it's monotonically increasing up to some 2000 100 Kelvin, and then there is a sudden jump is there, and after that again it is linearly increasing. So that jump actually marks the melting of the crystal. So that represents the melting temperature or the liquidous temperature. So the liquidous temperature here is 2094 Kelvin, and the red curve is representing the cooling curve. So the TL is written here, that is the liquidous temperature, that means where the crystal melts and becomes liquid. So that is the 2094 Kelvin for this aluminum zirconium alloy. To mark the GFA, that is the glass forming ability, we need to know the liquidous temperature and the glass transition temperature. And the ratio of these two gives us the glass forming ability of any crystal, any material. So TL is calculated from this melting curve, and then for TG, we have calculated it from this second curve, which is the radial distribution function. You can see it G of R, that is known as the radial distribution function. So that is basically, for the experimentalist I'm telling this, that is basically the Fourier transform of the structure factor. That means it gives the nearest neighbor arrangement of the atoms. So the first sharp peak you can see, so that is the nearest neighbor atom arrangement around a central atom. And the second and third peak shows you the next nearest neighbor, and like so on. So these are basically, you can see short range ordering is there. Black one is for the 294 Kelvin, then red one is 505 Kelvin. So it is in the order of increasing temperature. So at the highest temperature, that is 2496 Kelvin, you can see only the first peak is there, which is not so sharp, and the second peak. After that, it is just like liquid. So it is a melted structure. It is the GFR depicts a liquid structure. And as the temperature decreases, you can see here at the temperature of 1115, that is 1115 Kelvin, the second peak, okay, starts bifurcating. The two sub peaks arises at a temperature of 115 K Kelvin and below that. And at 505 and 294, you can see there are prominent two sub-peaks in the second peak. So that actually marks the glass structure, the glassy structure. So the glassy structures have a second peak which has two sub-peaks. And then short range ordering is there, no long range ordering. That means there is no crystal is formed. So this is a amorphous solid. And the TG, to calculate the TG, the formula is we have to plot the G mean by G max versus the temperature. So G mean is the value of the first minima in the GFR curve, and G max is the value of the first maxima in the GFR curve. So that ratio versus the temperature I have plotted in the insert picture, and then took the slope, and then that gives us the TG. So TL and TG, both of them will give me this known as the Went Abraham formula. So that is RA. Okay, so RA is G min by G max, and that gives me TG. And the TRG, that is the reduced glass transition temperature, you see here TRG is equal to TL by TG. So TRG is reduced glass transition temperature. So that value came out to be 0.532 in this case. So any value of TRG around zero point 0.5 marks the formation of bulk metallic glasses. That means these material are good bulk metallic glasses. Their glass forming ability is good. So this confirms the formation of bulk metallic glasses for the aluminum zirconium alloy. So this number 0.532 confirms that one. And after that, we have studied the mechanical property by applying different strain rates to the bulk AlZr3 alloy. So here I am plotting the stress strain curve to calculate the Young's modulus, yield stress and yield strain. So this is at various strain rates varying from 0.0005 picosecond inverse to 0.01 picosecond inverse. So y-axis is stress and x-axis is strain. So you can see the first one is the stress increases with respect to strain linearly and then reaches a maximum and then suddenly drops, and so that is the basic way of the stress strain curve. So first is the linear elastic region, then there should be a plastic region. If some ductility is there, after that there is the fracture point. That means it breaks. So here there is no plastic region, and that means they are more fragile because they are glassy materials, so they are more fragile. So there is a elastic region. The first linear region is the elastic region. That is the elastic limit where we calculate the Young's modulus stress by strain in that linear region. And after that there is the fracture point. The sudden fall represents the fracture point. So from this curve, the Young's modulus is calculated in the linear region by doing a straight line fitting and taking the slope of that stress by strain. So in this table I am presenting the Young's modulus, yield strength and yield strain with respect to the strain rate. So we have noticed that the Young's modulus decreases marginally with increase in different strain rate, but the yield strength and yield strain remains constant. So here I have plotted the Young's modulus with respect to the strain rate, and it shows clearly that there is a decrease in the Young's modulus with increase in strain rate. And okay, so this comes to the conclusion. So for this AlZr3 alloy, we have seen that Young's modulus decrease with increase in strain rate, whereas yield strength and yield strength showed no significant variation. Formation of bulk metallic glasses of AlZr3 is speculated from the RDF curves, that is the radial distribution function. The value of reduced glass transition temperature confirm the formation of good BMG, and the Young's modulus calculated for this BMG was around 89.76 GPa, and Actually, for the pure aluminum, the Young's modulus was 57, and for the pure zirconium, the Young's modulus was 98. So for the alloy, it is around 89. So this depicts that they have high mechanical strength because Young's modulus is a very good number, and they have the glassy property. So as I mentioned, they have application in various fields. So this study can be again extended to study the effect of temperature and the orientation and all those things to know how the mechanical property can change with respect to temperature and orientation and all those things. So this completes my presentation. So thank you.
Everyone. This is Sausurya from Bandari Ministry of Technology, Satyamangalam, Tamil Nadu. My topic is design aspect of lightweight building blocks using a novel mixture of nanomaterials for low-cost construction. My paper ID is 290. Now we're going to see about the project details, concept of the solution, scope of the solution, pros and cons of the solution, technical description, implementation plan, and testing and analysis, cost estimation, and references. In problem statement, reducing a dead weight of structure is a major challenge in construction industry. So when the foundation is subjected to seismic stress, that is an earthquake, the conventional bricks, the normal red bricks, may fail to bear the base shear. That is a shear failure which may get broken and the whole building gets damaged. So there is need to manufacture
Uh, Sorry, your voice is breaking. Sorry, am I audible to you? You please check your connectivity. Your voice is breaking. You please check your connectivity.
Yes. So now my voice is clear, sir.
And now it's clear.
So this is my problem statement. In problem statement, we're going to see reducing the dead weight of a structure is a major challenge in construction industry. When a foundation is subjected to seismic stress, conventional bricks, which may failure to bear base shear, that is a shear failure. And there is a need to avoid this. We need to manufacturing a lightweight blocks, which has a greater compressive strength and durability, and using a low cost natural recycled materials. The use of nanomaterials is manufacturing the lightweight blocks is one of the proper cementing techniques. The nanomaterials which we use, such as cement, sand, fly ash, limestone, gypsum, etc. This is the concept of the solution. Selection of nano-sized aggregates, which includes fly ash, gypsum, lime, cement, and alumina, is attempted using a top-down approach. An optimum mix ratio for these materials has been achieved in association with cement for design strength. And these lightweight plants were casted using a selected combination of nanomaterials and also tested in both mechanical and thermal properties for verification. And the prepared blocks are very lightweight, strong, and durable based on the test results. This is the scope of the solution. A normal combination of different nanomaterials consisting of natural, recycled, and industrial byproducts for preparing the lightweight building panels, and also determination of optimum mix ratio design suitable for selected applications. And also these can be directly applied for non-bearing member, that is the member which is usually non-reinforcement is used. Where the reinforcement not used, we can use this lightweight panels in any building constructions, and it is manufactured with a low cost compared to the normal red bricks or hollow bricks. Also, it increases the green building norms and ensures green building norms, and also improve thermal properties. The pros of the solution is considerable reduction in the dead weight of the structure, and also protection against the base shear under the influence of seismic force, that is earthquake force, and also it is increased in the thermal. carbon emissions usage consists the usage of the
Sorry,
massive construction
again
is
breaking. Sorry,
and to
sorry, am I
improve
audible
this
to you? Sorry, yes, your voice is still breaking. Again, it's breaking.
sir, is this up to this slide is my voice is okay, or shall I present one more thing, sir?
Yes. No, no. Up to this is okay. You can check your internet connectivity. No? During the presentation, your voice is breaking.
Okay, sir. So now is my voice is okay, sir?
Yes, your voice is now okay.
The disadvantage of the solution is the usage of construction these lightweight panels is massive construction which is in quotient, and these lightweight blocks need some public awareness to get it. And this is the technical descriptions. These are the raw materials which we use: sand, cement, fly ash, gypsum, limestone, and aluminum metal powder. And this is the process of mixing. After mixing, we have to cast the lightweight panel. And after the lightweight casting, it's next process demolding. After the demolding, and the process is testing. And this is the working model. In working model, which we use 4 ratios, which includes in ratio 1, cement, sand, lime, aluminum powder. And the mixed ratio is 1 is to 2.14 is to 0.71 is to 0.014. And in specimen 2, which is the choice of cement, sand, lime, aluminum powder, and sisal fibers. This is 1 is to 2.14 is to 0.7 is to 0.14 is to 0.014. And in specimen 3, we use cement, fly ash, sand, lime, coconut fiber, and which aluminum powder is the ratio is 1 is to 0.4 is to 3 is to 1 is to 0.2 is to 0.02. And in the last ratio is cement, fly ash, sand, scissor fiber, and we also use aloe vera gel, which is one of the natural product. And in coconut fiber, this is one of the natural product, and the aluminum powder. And the final ratio is 1 is to 0.2 is to 3 is to 1 is to 0.2 is to 0.02 is to 0.1. And these are the panels which I casted. Now we're going to see the testing analysis. There are 5 tests we done. 5 tests. There is a dry sinkage test, fire resistance test, density test, water absorption test, and the compression test. In a drying sinkage test, the volume reduced of lightweight panel, which is from 12,000 centimeter cube to 7,000 centimeter cube. This is a mix 1, mix 2, mix 3, and mix 4. In fire resistance tests, after breaking a specimen in particular hours, the specimen 1, which is break at 70 kilonewton per mm square, and mix 2 which is broken in 65 newton per mm square, and mix 3 which is broken in 45 newton per mm square, and mix 4 which is broken in 41 newton per mm square. In acid penetration test, we drop the panels in hydrochloric acid, and by checking the initial weight and final weight, which is to identify the weight loss. The mix 1 ratio is up to 800, and the final weight is 550. And in mix 2, the initial weight is 600, and after dropping into the HCl, the final weight is 400. In mix 3, the initial weight is 550. After dropping into the HCl, the final weight is 100 Newton per mm square. And mix 4, the initial weight is 550, and the final weight is 120. In density test, density this is by mass by volume. The mix 1 is up to the kg per mm square up to 0.7, and mix 2, that is a specimen 2, which achieves 0.8, 0.62 kg per mm square, and in mix 3, which attained 0.36 Newton per mm square, and mix 4, which attained 0.46 kg per mm square. In a compression strength test, the 4 ratios which withstand up to the mix 1 withstand up to 4 Newton per mm square, and in mix 2 withstand 3.7 Newton per mm square, and mix 3 withstands up to 3.46 Newton per mm square, and mix 4 which withstand up to 3.58. And now we're going to see about the cost estimation. This is the lightweight panel which we made, and this is the AAC block, which is available in market. The price of the cement is rupees 21 per kg, and the fly ash is rupees 1 per kg, and sand is up to 7.5. For this ratio is for one specimen, and the gypsum which is used for casting one specimen is rupees 5, and lime which is used for is 2.5, and aluminum powder is 5. The total price of the block is 42, and the block which available in market is 54. And these are my references. Sir, thank you, sir. Thank you for giving this one.
Okay, please start. Okay, very good afternoon to all of you. Before starting, I should thank the organizer for giving me the opportunity for presenting my research work, which will be on architecture of inorganic organic hybrid perovskites for enhanced stable photovoltaic performance. I am a faculty member of Calcutta University Chemical Engineering Department. Actually, I am working on the renewable energy sources, where I applied the different types of the perovskite material in the different purpose of the renewable device fabrications. So today's talks I'll cover about the sustainable solar cells, which will be the human health compatible and the sustainable development society friendly. So for this purpose, nowadays, you know, the silicon solar cells which is available in the market, the cost is so high. And for this silicon solar cells, we are trying to replacing the cheap material in place of the silicon, like perovskite solar cells and different types of the polymeric solar cells. But in the perovskite solar cell, there are a lot of problems still now, which we have to overcome for getting it commercializations. So here, my talk will start at the first, what is perovskite solar cells, why it is important, and what are the issues we need to overcome for application purpose in the solar cells for commercializations. So here, if you see this perovskite materials is one of the important materials we can use for the renewable devices like water splitting applications for fabrication of the electrode, for solar cells fabrications are the different types of the thin layers on the surface, and also the polymeric electron fuel cells and the multiple memory devices. So this tuning is possible in the perovskite solar cells, as the structural tuning is possible by doping in the perovskite materials with other materials in this case. So in my labs, I am working the different types of nanostructure formations of the perovskite materials, 2D, 1D, 3D dimensional nanostructure, and also the composite perovskite structures. And we applied these types of the nanostructure perovskite materials in the renewable solar energy fabrications. So if you see the perovskite materials, that is structure actually MaX3. It is the common structure where M is a inorganic organic cationic material, and the A is the body centered, and B in the X is the halide material. And here, if you see the why perovskite materials is important, here is you can use the large absorption spectrum and adjustable band gap possibles, inexpensive, and the large power conversion efficiency is have. So if you see the market, different types of the perovskite materials available like inorganic halide, intrinsic perovskite material, doping perovskite materials. So choosing the platforms of the perovskite materials, if you see the organic, inorganic, hybrid perovskite materials, you can easily tune the band gap for applications of the solar energy purpose for using the solar fabrication devices. If you see the structural side, A side, B side, and the halide sides, we can easily dope different types of the cationic material, and the B side also different types of metal cationic materials for tuning their properties. So in this case, if you see the solar cells, we know that there is PN junctions in the solar cells fabrication process, where the silicon is an N-type and P-type silicons, and merge these two, and middle the boundary layer is there, then falling the photons, and it convert the electricity. So here we replace the silicons by the perovskite materials. If you see the trend in the perovskite materials in the applications of the solar cells, nowadays you see the trend would be comparing with the others like crystalline, polycrystalline, and other materials. So perovskite materials application is dramatically increased, and it's reached the efficiency around 28.2%. Currently, it is informed in the tandem solar cells, which is reported by the King Abdullah University in Saudi Arabia. So it is dramatically increased. Why it is increased? Because of this fabrication process, easily tunable process, and its absorption coefficient is much higher, and we can use the band gap property very easily. We can tune this. But till now, what are the challenges is the perovskite material? Perovskite material is not stable. We need to sustainable perovskite material. We have to synthesize the perovskite material to overcome these challenges like stability, degradations, and increase the efficiency, low-cost manufacturing process required, and the validation and for commercialization. These all parameters we need to overcome for commercializations of the solar cells, perovskite solar cells. Now, if you want to select the perovskite material, define that the perovskite materials already applied for the solar cell fabrication, but not are still commercialized because of some of the problems like it is degraded with time, and it is toxic material some of the introducing, and also some cases it's absorb the moisture from the air. So many problems are there. So when we are fabricating the solar cells by using the perovskite, we select the material from this structure with proper band gap material. Then we define that the doping material, and then we fabricate the solar cells. And for the fabrication solar cells, we take the tolerance factor, because tolerance factor is most important, because if the factor is stable, because T value is between 0.89 to 1, that means the material, this material is stable. So that material we can apply for the solar cells fabrication process. So these challenges we are trying to overcome in my labs. The halide perovskite materials nowadays inform maximum efficiency. So we try to eliminate the lead material from the halide structures because it is carcinogenic, and it is a health issue also be there. And also the lead perovskite are unstable because of the moisture, heat, and UV radiations. So these things we try to overcome in my labs. So if you see the lead, in the lead material is very important in case of the solar cells, which is giving the very good efficiency for the solar cells because of its band structure. So if you see the periodic table, when you go apart from the lead, this SN and gallium, this is the moisture sensitive, and when you go the bottom, and this is also the radiative. And when we go the left side, all the materials, these materials is the valence is different, so defect formation is happening. So selection of the replacement of the lead material is very important, so that it gives the proper stable perovskite sustainable solar cells. So also that the moisture stability, when you stay the lead iodide solar cell, lead iodide come out from the systems with presence of the moisture. So if you see this our fabricated solar cells, when you keep these solar cells after preparing the thin films, after 60 minutes, its color is changing and getting pale yellow. That means lead iodide is coming out. That means it is not stable. So our target to make these stable solar cells so that it can stable for long time for the applications purpose. Also, if you see the absorption coefficients, it is also getting down after keeping in the long time. So this stability issue we try to overcome in my labs. So here, if you see different types of the perovskite materials and with doping, we are adding in the systems. Also, we are heating these materials and try to make it stable in the ambient condition. So if you see the different types of perovskite materials, if you see the FAI, MAI, here FAI is much more stable in case of the compared to the perovskite materials. Now, how we can improve the stability of the solar cells and how we can replace the lead with other environmentally friendly materials. In my labs, I am putting the SN in place of the lead, toxic lead materials, and we change the percentage of the lead SN in place of the, and we check the efficiency of the solar cells. This is the fabrication process and synthesis process of the SN-based perovskite materials, and this is the sol gel process we are using. And after spin coating, this is the fabrication techniques of the solar cell fabrications process. I am not describing these steps. After fabrication, we check the stability and tolerance factor by XRD, and then you see the after changing the percentage of the SN, certain percentage, it is giving the best tolerance factor around 20% SN. We are giving the most stable tolerance factors. And the XRD we did for getting the purity and other crystallizing property checking for the solar cells. And then we do the optical property checking, where the maximum absorption we can get, we see that 20% SN is giving the maximum efficiency. And after changing the SN, also we see the structural morphology also changing in the systems. It is going to define types of the nanostructural materials, when we increasing the SN percentage in the solar cells. So this is the structural output results finally in our SN-based solar cells, where we can see about around 20 or 30% SN is giving the maximum efficiency and fill factor. And this is our fabricated cross-sectional views of the solar cells thin films, and this is the IV characterization and performance analysis of the solar cells. So here in this case, this paper is published in the SES energy journals, energy letters. And from here, we can conclude that the optimized percentage of the SN around 20 to 30% is giving the maximum efficiency of the solar cells. Like this way, different types of the study we also done. We changed the fabrication techniques, like thermal engineering techniques we use to fabricate these SN-based solar cells and try to improve the efficiency of the solar cells. And this is the thermal engineering technique, where two types of the thermal heating we did inside of the thin films for making it more stable. And finally, we check the efficiency increase in the dual stage thermal engineering systems, and it is giving the efficiency around 12%. That is much more than the comparatively study. Then if you see the IPC, it is giving the 84% IPC value in case of the dual stage thermal engineering process. So here we can conclude in the SN-based perovskite solar cells, we are optimized the performance of the SN-based solar cells for replacing the lead with SNs, and we take the performance analysis of the solar cells. Till now, some of the problems is there. The oxygen exposure is remains still as challenges. When it is open in the oxygen atmosphere, it's getting down and degraded properties increasing. So we need to overcome these things. And also, we are putting different types of dielectric material in the solar cells as a capping agent, so that the lead iodide should not come out from the systems, and it's giving the much more stable solar cells. So here, difference of the structural morphology with putting the dielectric material in the solar cells. We have done the TM, where the nanostructure, nano rod is coming in the systems. So here, if you see the analysis with the dielectric material, it is giving the efficiency less, but it is stability much more increased. It is stable much more compared to the initial I reported. 1 month around, it is much more stable. And lastly, for the low-cost fabrication techniques, we are using different types of the biomaterial, like carotene-rich biomolecules, and also the spinach-rich biomolecules as a pigment material in replacing the inorganic material in case of the solar cells, and making it low-cost solar cells. And for this, I am going to the final output results of this fabrication process, where we did this all the optical properties, and this is the result of the bio-based perovskite low-cost fabrications material techniques to making the solar cells. Here, the efficiency is not much higher, but the cost is the solar cells much more less compared to the organic made perovskite solar cells. So here is the conclusion. In that case, in the dielectric extracted organic dielectric dyes are much easily we can put inside the material inside the perovskite and make it much more easily cheap materials as a solar cells applications. And then finally, we did some of the simulations with the available software, SCAP software. And this simulation study, we get the defined of the fill factor efficiency. And finally, we check the simulation study with the experimental study, and we match the simulation study with the experimental study, so that we can get the actual value of the simulated result in practically or not. We get around the 5% error in case of the simulated value. And lastly, I'll describe some of the rice husk related crystalline nanosilica, which extracted as a sustainable material for the solar cells applications. Here we extracted the silica.
Sir, please, Dr. Subhashis, please conclude.
Yeah, this rice husk nanosilica we applied in the solar cell. We did all the optical properties, absorption properties. Finally, this is the current electric optical properties and the electrical properties. It is showing around the percentage of maximum efficiency 2.1 in case of the rice husk related nanosilica. So here I conclude finally, sustainable solar cells is very important, as the toxicity is there in the lead related materials. So we replace the lead with the essence, and the biomolecules extracted pigments in case of the lead material, and we try to improve the efficiency of the solar cells. So if you see that in the future challenges the perovskite solar cells, as it is increasing the efficiency dramatically, we think 2030 onwards the perovskite solar cell will come in the market and to replace the silicon-based solar cells. This is some of the list of the publications from my lab, and I should thank the funding agency ICRTMD for funding my laboratory and my PhD scholar Orgode and Abdul Moez. Thank you very much.
Yeah, thank you very much, ma'am. Good evening, all. So I am Professor Jayaprakash from Center for Bioseparation Technology, Vellore Institute of Technology, Tamil Nadu. So here I am going to present our work on synthesis, characterization, and biocompatibility of macroporous polyhydroxy ethyl methacrylate based cryogen. So you can see there are three people here down. I'm Jayaprakash. Another one is Kishore, Associate Professor Kishore. He is our polymer chemist, and Jyoti Lakshmi, she is my PhD student. So before letting into the subject, let me tell you what are cryogels. Cryogels are three-dimensional polymeric scaffolds formed at sub-zero temperature and essentially consists of an interconnected network of macropores. So here in the picture, you can see the process of making cryogels. So it starts with a monomer along with initiator solution, and you do the freezing below 0 degrees centigrade, which leads to cryogelation, and followed by thawing. And this thawing will make cryogel with interconnected macropores. So our major goal is to develop new cryogel material of simple chemistry using less toxic monomers, and also to develop an in-house bioreactor system using the above cryogel material to improve the production of high-value proteins like monoclonal antibodies using mammalian cells. Because I am an immunotechnologist and I develop monoclonal antibodies, in-house monoclonal antibodies. So we want to improve the production of monoclonal antibodies using these cryogel materials in the bioreactor system. So if you see the advantages of these cryogel material, the first advantage is a rapid swelling time, usually below 2 minutes. And this will reduce the pre-equilibration time with the media. And also it will facilitate a homogeneous cell seeding and also distribution. And another advantage of this cryogel material is it is super macroporous, which will aid in efficient cell immobilization. And if you see the pore size ranges from few micrometers to hundreds of micrometers. And it will also give a congestion-free media flow, and also ease of nutrient availability for the growing cells. So we prepared cryogel with the monomers like 2-hydroxy-ethyl methacrylate and allyl glycidyl ether with methyl bisacrylate as cross-linker. And you all know that this hydroxy-ethyl methacrylate is more hydrophilic and also biocompatible. And AGE provides epoxy groups for gelatin immobilization. So the immobilization of gelatin on the cryogel matrix, it actually helps in cell attachment, and also it allows cell growth as a confluent sheet inside the cryogel matrix. So these monomers are comparatively less toxic and ease of preparation, and we can also make a different format of these cryogels. We can make tube-shaped cryogels as well as disc-shaped cryogels. So these are the monomers, cross-linkers, and initiators what we have used for making our cryogel material. So here you can see the ammonium persulfate reaction catalyzed by TEMED. So with these monomers, cross-linkers, and initiators, we prepared the disc shape as well as a tube-shaped cryogel material. And after preparation, we did the characterization, like physical characterization, chemical characterization, and biological characterization. So physical characterization, we did a SEM scanning electron microscopy, porosity and flow property. And chemical characterization, we did the conformation of epoxy groups and protein absorption studies related to direct immobilization of gelatin and long linker immobilization of gelatin. And coming to the biological characterization, we did the in vitro compatibility with the hybridoma cells and as well as CHO cells. So let's see the physical characterization, what we got in our study. So this is a scanning electron microscopy of our cryogel matrix. So here you can see the macropores interconnected within the cryogel material. And we did the swelling property and we got the porosity up to 93.8%. And if you can see here, the degree of swelling is 15.3 grams of water per gram of gel. So here in this picture, you can see both the wet gel as well as dried, the same dried gel, cryogel material. So in order to study the pore size distribution, we did the mercury intrusion porosimetry method. So, and by that method, we could find out the pore size distribution, and it ranged between 17 micrometer to 59 micrometer. And we found that surface area was around 0.9 meter square per gram of this cryogel material. And we also did the flow property under the physical characterization. So here in this graph, you can see as the flow rate increases, the pressure also increases. So we have done the flow rate property with both cryogel with gelatin immobilized as well as cryogel without gelatin, but both showed the same flow property. And coming to the chemical characterization, we did the protein absorption studies, especially gelatin immobilization. So why gelatin? So gelatin, it provides a microenvironment for the proliferation of cells, and it is highly biocompatible and also biodegradable. And it is well suited for mammalian cell lines, especially for hybridoma cell lines, which produces monoclonal antibodies as well as CHO cells. So we did two approaches for immobilization. One is direct immobilization. Another one is long linker approach through glutaraldehyde. So here you can see in this PPT, the direct immobilization of gelatin and also another method using a long linker approach. So to conclude with this immobilization, we found that long linker approach for gelatin immobilization, it gave a higher amount of gelatin to the cryogel material. So we we used the long linker approach for immobilization of gelatin to the cryogel material. And we also did the confirmation of epoxy groups. So we found that increase in epoxy groups happened with increase in allyl glycidyl ether. So this graph, you can see the percentage of allyl glycidyl ether increasing, and also you can see as the concentration of as a percentage of age increases, that is allyl glycidyl ether increases, the number of epoxy groups also increases. So this slide concludes the porosity and swelling degree and gelatin immobilization optimization study. So with the optimized condition, we found that cryogel with 1% allyl glycidyl ether exhibited good porosity, swelling degree, and gelatin immobilization is found to be significantly effective. And finally, we did the biological characterization of the developed material, cryogel material. So here, what we did is we did the growth of hybridoma cells, which produces monoclonal antibodies. And also, we also did with another cell line CHO cells with this cryogel matrix for 15 days under static culture method. It was done in 24 well plate format. So here, the proliferation of cells were measured by MTTSC, 570 nanometers, and production of monoclonal antibodies by hybridoma cells were measured by indirect ELISA method, that is absorbance at 450 nanometer. So as a control, we had 24 well plate culture without this cryogel material. And all the cryogel materials which were used in this study were ethanol sterilized. So this is the result which we got in the biocompatibility study. So here you can see this bar diagram indicates the monoclonal antibody production both in the control as well as the well with the cryogel material. So the production of monoclonal antibody, it was not affected by the by these cryogel material. And this line graph, it shows the cell viability. So green indicates the control, that is control well with without cryogel, and this purple one, it is with well with the cryogel. So one advantage with this, you can see here in the control, you can see there is decline in the cell viability after 8th day, whereas it maintained in the test which had a cryogel material. And we also did the biocompatibility of this cryogel material with CHO cell lines. Here also we found it is highly biocompatible. So here you can see blue color one, it is a control 24 well plate without cryogel, and this orange or red color, it is a 24 well plate with cryogel material. So it gave more or less similar cell viability. So with this, we can conclude that these cryogel materials are highly biocompatible with the cell lines which we used for our study. And we prepared a tube-shaped cryogel matrix with 2 centimeter height and 0.9 centimeter diameter with a bed volume of 1.27 ml. And also, we also made a disc-shaped cryogel matrix of 0.8 centimeter height and 3.5 centimeter diameter of bed volume of 8.65 ml. And we, in fact, with this material, we have done a study. We developed a mini bioreactor setup with these cryogel matrix. Okay, and we did the culturing of hybridoma cells producing monoclonal antibodies, and we observed that the monoclonal antibody production was 10 times higher than the normal static flash culture method. So this cryogel material, whatever we have developed here, it is highly biocompatible. And it was found to be very good in production of producing monoclonal antibodies using hybridoma cell lines. And we have this part of work I'm not presenting. We have already communicated to a paper and it is under review. Thank you. Thank you.
You can integrate heterojunction in the chip itself. That would be more advantageous because it would be saving much more fabrication procedures, so that you can get the fabrication procedure is less, and then you would be able to synthesis is much more easier in that case. So what we have done is that we know that silicon nanowires, if you have a silicon porous as a substrate, if you etch chemically, they can often lead to very beautiful
Hello,
Hello?
Madam Sujeta, please switch on your camera.
Okay, 8 minutes. Sorry.
So all the presenters are requested to please switch on their camera when during the presentation.
Okay. So yeah. So we if we have this silicon as the substrate, so the one-dimensional instruments each they can be easily chemically etched to form one-dimensional structures over a large area very uniformly, and this because of the one-dimensionality, they provide vectorial pathways for easier charge transport. And if you have the heterostructures on that, then they have a larger interfacial area where these heterostructures can be formed. So in our group, we have synthesized silicon nanowires over a much millimeter by millimeter size area, quite uniformly by MES technique, metal assisted chemically etching technique, where it is etched with the help of AgNO3 and HF. So in this work, what we do is we try to decorate the silicon nanowires with other metal chalcogenides to produce new properties. So one, we will be dealing with silicon nanowires and CDS, which will be used for humidity sensing, and also for subsequent power generation from the moisture. And for the other, we will be seeing for the silicon nanowire PVS heterostructures, which can be used for ammonia sensing and also can be used as a self-powered photodiode material. To fabricate these heterostructures, we have taken help of this chemical bath deposition. It is nothing but we have the beaker, we put the substrate, and in that we put the deposition solution with the precursor material. So suppose we are putting cadmium sulfide, synthesizing cadmium sulfide, we put the cadmium precursor and the sulfur precursor, and we put it in a water bath to have the achieved temperature. And we can have the deposition temperature can be varied from 0 to 90 degrees centigrade, and the deposition time we varied for several hours according to our own wish, and the films are grown over the substrate in this way. So this chemical bath deposition, the advantage of this is that it is a very slow process, simple process, low cost. You don't need stringent vacuums or plasma generators like MB, and you achieve, if your substrate material has an epitaxy, a quite substantial form of epitaxy is obtained from the films which are deposited on that also. One of the disadvantages that you have a lot of solid waste, but things are, for some pros you also have some cons. So because of its very simplicity of the process, it is quite widely used. Now, in the chemical bath deposition, there are generally two types of mechanisms that are observed. One is called the cluster mechanism, where if you have, suppose, growing lead sulfide material, then your leads and the sulfide ions are present in the ion itself, and then they form get deposited on the PBS coating, or PBS formed is in the solution, which then gets attached to your substrate. So this is kind of the clusters which are formed in the solution. They get attached to your substrate itself, and hence the name cluster mechanism. On the ion by ion mechanism, however, you have the substrate upon which the leads or the sulfide ions, they are being attached, and the PBS grows on the substrate itself. Obviously, the ion by ion mechanisms helps to achieve a better crystalline growth in that sense, and usually occurs at higher temperature. In the chemical bath deposition, the main parameters that we tend to vary are the temperature, the pH of the depositing solution, the time, and also we can add the complexing agent, which we will be kind of complexing the the metal ions preferentially, and hence they would be kind of controlling the release rate of these metal ions. To start with, for this first case, where we will be growing this piece silicon nanowire cadmium sulfide heterostructures, we have this is the schematic synthesis video. We started with the silicon wafer, and then we deposited AG. On that, we by we and H2O2, we chemically etched the surface of the silicon wafer to produce uniform silicon nanowires. And on that, if we followed the chemical bath deposition with the help of cadmium precursor and sulfur precursor, these silicon nanowires are kind of uniformly coated with cadmium sulfide nanoparticles. These are the same images. On the B, it is kind of the pristine silicon nanowires, and C is the silicon nanowires after coating with cadmium sulfide. If we do a DAX of that, we can see that the cadmium sulfide are almost present in the stoichiometric ratio and uniformly distributed over this entire area, which shows that they are uniform coverage of the individual silicon nanowires that are thick. Now, cadmium sulfide is itself known to be a very hygroscopic material. So they are very popularly used as humidity sensors. So what we did is we tried to extend it more. We put the device of this cadmium sulfide and silicon nanowire heterostructures inside a humidity chamber. We tried to vary the water humidity inside this vessel by controlling the water glycerol mixture, and we tried to measure the voltage which is generated. We saw there is a voltage generated across this junction, PN junction, and we tried to measure the voltage and the current which is generated. What we saw is that with the change in the relative humidity, there is a buildup of this output voltage and also the output currents that are generated, and they are found to be quite reversible. That is, if you put it on, they quite achieve to a very high value, and if you put it off, they kind of gain retain back their original value with a response time, with a response rise time and a fall time of 50 seconds. As so they can be utilized to achieve a highest output voltage of around 300 millivolt and a current of in current is slow at nanoampere ranges, and this maximum output voltage can be varied by the amount of deposition, varied by the varying the deposition time of the CDS. So if you kind of deposit it for say around 60 minutes, it achieves the highest output voltage of around 300, and with the increase in the CDS deposition time, the output voltage decreases. Similarly, we tried to do it for this PBS ones. So here we also followed the same. We had the silicon substrate. We produced silicon nanowires, and on that we deposited PBS nanostructures to get uniformly coated. These are the same images, and TDAX, which shows that PBS is uniformly coated over the silicon nanowires. But here what we did is we tried three different conditions. One is over the bare silicon, one is over the silicon nanowires with the PBS, and the last one is where the silicon nanowire along with PBS, we put a complexing agent of citrate to control the growth rate. And what we measured kind of tested it for ammonia sensing in the resistive mode. So what we saw is with the increasing ppm of ammonia, the current in IV curves increases, so the resistance changes, and with it is consistent with the concentration of varying the concentration of ammonia, and it is reversible. It comes back to its original value once the ammonia is switched off. And also, most interestingly, among the PBS over the silicon, of the three samples that we had, that is one over the PS silicon substrate, one over the silicon nanowires, and other with the silicon nanowires with the presence of complexing agent. The last one in presence of complexing agent shows the maximum responsivity.
Madam, please conclude.
Yes. Shows the maximum responsivity because of surface passivation. They can be, this was in resistive mode. Further, they can, since PBS is known to be a IR sensor, we tried to explore it for IR photodiode applications in the photovoltaic mode, and we saw that even in the self-powered mode, they have quite a substantial amount of photocurrent which is generated, and this is because, which varies with the bias, and this is because across this PN junction you have a substantial voltage which is generated, which is around 30 millivolt, which is generated. So we have been successfully synthesized silicon nanowires and PBS and CDS heterostructures for various different applications. These are the publications if anybody is interested with. And I would like to thank SCRB, Government of India, for granting me the fellowship for carrying for the Bridge Power Grant, my student Rinki and Alisha, and my colleague Dr. Raki Grover, Dr. Nitish, and Dr. Vivek, and Dr. Vicky Jain, our director, and all my colleagues of my department. Thank you.